Hello and welcome to this new video where we talk about mathematics and physics on the board. Today what we are going to talk about is something logarithm. Today is something quite common, and it has to do with how do we calculate, if they exist at all, the logarithm of negative numbers. Now this is something that you may have not come across if you are either in an applied math or engineering or physics degree where you haven't had an exposure to a full kind of complex analysis course. Indeed in physics that's quite uncommon to see it. However, the goal here is going to see in a very, let's say, simple way how we all have calculated in many instances the log of a negative number without realizing it, or at least we could calculate it very easily. And then I'm going to generalize upon this afterwards, and we'll see how that would work for any complex number. Right, okay, so let's start with the basics. The logarithm, so the natural logarithm so-called, is defined, and on purpose I'm not stating here what would be the domain definition of x, etc., but that's essentially the inverse function of the exponential function. So what that means is that the natural logarithm applied to the exponential of x is going to return x. Okay, so that's the basic definition of it. And in principle, once you have set out like the domain of definition of x, then you can try to determine what the corresponding domain of definition of the log. But again, I'm going to suspend that a little bit. And what we are going to look at is this particular case. Now, this equation here is a very famous equation that usually people would have seen perhaps at the level of A levels, or if you have studied complex numbers, so not necessary to have like any complex analysis background at that stage, complex numbers where there is a connection that is drawn between the exponential function and the cosine and sine functions. Okay, so that's something that is very important. Some people say that this is the most important equation in mathematics, or at least one of the most. And so you see how very important it is. Now, one of the things that we can do is try to see what exponential of I pi is going to be. So if I substitute pi in there, so pi radian here, you're going to get cosine of pi plus I sine of pi. Now, you probably know, otherwise you can check your own tables, that this particular sine of pi is going to be 0, and the cosine of pi, it turns out to be equal to -1. Okay, so the bottom line is that exponential of I pi is equal to -1. Now, what we can do is try to say, okay, let's try to apply a putative logarithm function onto exponential of I pi. So I'm going to say, let's assume that there is a logarithm function that can take as an argument the exponential of I pi. And what I know is that this is going to return from the definition of log, this is going to return I pi. Okay? But what I know as well from there is that exponential of I pi is equal to -1. So what I actually get is that I've got the log of -1 turns out to be equal to I pi. Okay? Now this is very interesting, because what that means is that the logarithm of a negative number is actually returning an imaginary number in complex number notation. So what I can say is that this thing actually belongs to the complex numbers, and in fact to the imaginary line of the complex numbers. Therefore, the traditional claim we're making that there does not exist the logarithm of a negative number is true insofar as we work in the reals, but as soon as we work essentially in the complex plane, then essentially we return an imaginary number. Okay, now let's try to see how that would work in general. Now, what we want to do is to benefit as much as possible from the properties of the way to write complex numbers as exponentials. That's so-called exponential representation of complex numbers. And so what I'm going to do here is that for any complex number, so for any complex number z, and you can imagine this as x plus iy if you want, then for any such complex number, we are going to get that z can also be written as the modulus of z, and then exponential I, and then phi of z. And the phi of z here is called the phase of the complex number, and this term here is the modulus. Okay, or sometimes this is called the argument as well of the complex number. Okay, so if I actually have a complex number that has this particular shape, then what I can do is simply say, well, I can apply the log to that particular complex number. So I've got the log of z is going to be equal to the log of the modulus of z. So that's not, this thing is a real positive number here. Then exponential I phi of z. And then that's what it is. Now, the next step is to basically use the property which is assumed here to be maintained. And this is something that I must say I'm not going to prove, is that we still assume that the property of log of a b is equal to the log of a plus the log of b. And in fact, that's for, here I'm going to assume that this is for any a and b, which are in the complex plane. Again, this is not something I'm proving. You could argue that this is a property I want to maintain from the logarithm in the reals. Okay, so let's say this is a complex extension of the traditional logarithm function, and so I want to extend as well as many properties as I can from the reals into the complex. So once I've done that, then therefore I can write that the log of z is equal to, for any complex number, is equal to the log of the modulus of z, and then plus the log of the exponential of I phi of z. Again, phi of z could be called arg of z, and then what you end up with, by definition of log of exponential, log of the modulus, and then plus I phi z. Okay. So basically, that's the result. So this is, and what you see here is that this thing here is real, so belongs to the reals, and this thing here belongs to, so that this is, so this term here belongs to, in principle, any kind of real number if you want. There would be some form of modulus in a sense, because there is some regression, but at the end of the day, this is imaginary. Okay, so this is an imaginary part. So this one is a full complex number. Okay, it's neither just real or just imaginary. It's actually the combination of both. Okay, so what we have finally is essentially, if I recognize that a negative number, what is a negative number? Basically, it's something that is going to be, so a negative number and how I'm going to call that, I'm not too sure. Let's call that actually x minus, just to say that this is negative. And so x minus is going to be, and so that's belong to the real. However, I can always write it as the absolute value of x minus, okay, and then exponential of I pi. Okay, so I can always write this x minus, which is always going to be a negative number, as being the modulus times exponential of I pi, which we have seen was equal to -1. So then in the end, if I actually apply this formula there, I get that the logarithm of any negative number x minus is going to be the log of the absolute value of that negative number, and then plus I pi. Okay, where pi here is the argument of the complex number. And there you go. Essentially, with that, you're able to calculate the log of any negative number without any problem. Now, there still remains that although you can calculate the log of negative numbers and so on, the log still remains undefined at 0. Okay, so at 0, things blow up nonetheless. However, as soon as you've passed 0, then you can define in the complex plane essentially the logarithm of a negative number. So that's it for today. If you've got any questions or comments, please let me know in the comment section, and otherwise see you in the next video.